In this video, we are going to discuss absolute and conditional convergence. So, definition of absolute convergent is absolute means already we have discussed it. Absolute means we need to ignore the means absolute value means we need to consider the modulus. We need to apply modulus of the series. Absolute means we need to ignore the negative values. If you apply the modulus, then we are ignoring the what? Negative values. We are combining it, right? So a series summation un is absolutely convergent. When it is convergent, if this summation over modulus un is convergent, then I can say that summation un is also absolute convergent, right? So another definition of conditional convergent, or I can say that summation un is divergent when summation of modulus un is conditionally convergent, right? Absolutely convergent and conditional convergent definition. So absolute convergence means what? If you say, suppose if you take summation un is a convergent series, then summation modulus of un is also convergent, then we can say that it is absolute convergence. And when we are going to say that the given series summation un is conditional convergent or divergent, if summation un is convergent, then summation of modulus un is conditionally convergent, means it is divergent, but for some condition it is convergent. So that's why we are going to say that conditionally convergent. Okay, so let us discuss about these two examples, and even we are going to solve some problems regarding these two concepts, absolute and conditional convergence. So in the note, what they have given, summation un modulus un is a series of positive terms. See, summation modulus of un is a series of positive terms, right? Summation un may be anything, means alternating series or positive series or anything, right? But summation of modulus un, whenever you are going to take absolute values, definitely they are positive, because we are going to ignore the negative values because we are applying modulus, right? So let us discuss a theorem regarding these concepts. So every absolutely convergent series is convergent. Every absolutely convergent series is convergent. See, absolutely convergent means what? Summation, if summation un is convergent, obviously modulus of summation of modulus un is also convergent. That is the definition of absolute convergence. So what is this statement? Every absolute convergent series is convergent. Every absolutely convergent series is convergent. So in this concept, in this theorem, what we need to assume first, we need to take absolutely convergent series and we need to show that it is convergent, right? So after that, we are going to discuss whether the converse part of this theorem is true or not. Let us prove this statement. Let summation un be an absolutely convergent series, then modulus of summation un is convergent. See, summation un be an absolutely convergent series, right? So absolutely convergent series means summation modulus of un is also convergent. Definitely it is, right? summation un is absolutely convergent, they have already given, and that series we are going to show that convergent, absolutely convergent and convergent, right? So we are taking summation un is absolutely convergent, and we are proving that summation un is convergent. That's it. So if summation un is absolutely convergent, obviously modulus of un, summation over n is equals to 1 to infinity, modulus of un is also convergent according to definition. So by Cauchy's general principle of convergence, we have for every epsilon greater than 0, there exists a positive integer m such that modulus of plus 1 plus plus 2 plus so on plus un is less than epsilon for every n greater than m. So it is the statement of Cauchy's general principle of the given series, right? So but according to the definition, what we have, modulus of un is convergent we have. So if I apply the Cauchy's general principle for this modulus of un, then what will get? Modulus of modulus um plus 1. Why it will get modulus of modulus? According to the theorem statement, Cauchy's general principle of the series, what is the statement? If summation un is convergent, modulus of plus 1, plus 2 plus so on un is less than epsilon. That too what? For every epsilon greater than 0 and for every n greater than m. That is the actual statement of Cauchy's general principle. But here we are considering modulus of un, no? We are concerned with this series. So therefore modulus of modulus will come. So terms are here in modulus. So modulus of modulus um plus 1, modulus um plus 2, so on plus modulus un is less than epsilon for every n greater than m, right? And if I remove the modulus, then also modulus of plus 1 plus modulus of plus 2 plus so on plus modulus of un is less than epsilon only. So for every n greater than m will get, right? Because all the elements are positive. So if I remove modulus, then also there is no alter in this term, alter in this inequality. So therefore modulus of plus 1 plus plus 2 plus so on plus un is less than equals to, what I can write down is modulus of plus 1 plus modulus of plus 2 so on plus modulus of un is less than epsilon. So this is according to Cauchy's general principle, and this is what we have got from the given series when we have applied the Cauchy's general principle for the modulus of un. Here for modulus of un we will get this inequality, but according to Cauchy's general principle we have this one, and also we are applying the property of modulus. So I can split these terms. How? Modulus of less than equals to, it will get less than equals to modulus of plus 1 plus modulus of plus 2 so on modulus of un which is less than epsilon. Already we have this is less than epsilon, right? So therefore I can say that this is less than epsilon, and hence by Cauchy's general principle of convergence, summation un is convergent. What we have taken? Modulus of modulus plus 1 and modulus of plus 2 so on plus modulus of un is less than epsilon we have taken, and what we have shown, modulus of plus 1 modulus of plus 2 plus so on modulus of plus un is less than epsilon for every n greater than equals to m we have shown. So that means what? We have taken absolute convergence, means modulus of un is convergent we have taken, and we have shown only un is convergent according to Cauchy's general principle of convergence, right? So therefore I can say that summation modulus un is convergent, hence summation un is convergent. So what is the ultimate conclusion is every absolutely convergent sequence or series, every absolutely convergent series is convergent. So this theorem is important, and they can ask, is every convergent sequence is absolutely convergent? See, is every convergent series is absolutely convergent? So my answer is no. So it could not be, right? It could not be absolutely convergent. The converse of this theorem I am discussing, right? Is every convergent series absolutely convergent? So no. So here we are giving an example of converse of the theorem, right? So convergence need not be absolutely convergence. So that is the converse of the above theorem, right? So for this we have to give a counter example. So therefore we have given here, consider this series, alternating series we have taken, summation over minus 1 whole raised to n minus 1 divided by n, right? So 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, the elements of this given series, alternating series, right? So un is equals to, if we consider according to alternating series, if they have given, you need to apply Leibniz theorem. So what is the statement of Leibniz theorem? If you want to say that the alternating series, obviously Leibniz theorem is on alternating series, right? So therefore whenever the alternating series is given, then you can apply Leibniz theorem. So what is the statement? Summation 1 whole raised to n minus 1 or n into un is convergent. When it is convergent, there are two conditions. Un is greater than equals to un plus 1, and second one is limit as n tends to infinity, un is equals to 0 we should get. So if these two conditions are satisfied, I can say that summation un is convergent according to Leibniz theorem. So let us see, here un is equals to 1 divided by n we have taken. Clearly un is greater than 0, right? And 1 by n is greater than 1 by n plus 1, un plus 1 we have considered. Un is greater than un plus 1. So first condition is satisfied of Leibniz theorem. And second condition is what? Limit as n tends to infinity, un is equals to 0 we should get. So if I apply limit as n tends to infinity for un value is 1 divided by n we have taken, limit as n tends to infinity 1 divided by n is equals to 0. So these two conditions are satisfied. So by Leibniz test, minus 1 whole raised to n minus 1 divided by n converges, right? So what we have shown, what we have taken, convergent we have taken here, summation un is convergent we have shown, but what we need to show that it is not an absolutely convergent, it is not an absolutely convergent series. Converse of above theorem we are proving, right? So if it is proved, we need to prove it. The converse of above theorem is not true. So if it is not true, we need to give a counter example. So therefore this is the counter example. What we have taken, summation minus 1 whole raised to n minus 1 divided by n we have taken as the alternating series, and what we have taken, un is equals to 1 divided by n, nth term, and n plus 1th term we have taken un plus 1 as 1 divided by n plus 1. So first condition is satisfies and second condition satisfies. Therefore by Leibniz test I can say that the given alternating series is convergent. So first part is over now. Second part is what we need to show that it is not an absolute convergence, right? So how we are going to show that? See here, but summation, what is the given series? They have given absolute convergence means in terms of modulus you need to put, right? So if I put summation modulus of minus 1 whole raised to n minus 1 divided by n is equals to, if I put modulus, definitely will get positive only. So therefore summation 1 divided by n will get. This alternating series will be normal series will get. Normal series means only positive values will get. So therefore summation 1 divided by n. So this summation 1 divided by n is divergent. Why it is divergent? Why it is divergent? See, 1 by n, it is in the form of p series, right? It is in the form of p series. What is the value of p? P is equals to 1 here. So if p is equals to 1, according to harmonic series, or I can say that p series, it is divergent, right? So therefore it is conditionally convergent. Therefore it is conditionally convergent. So it is not convergent. Absolutely convergence means it is not convergent. We have shown it as conditionally convergent. It is not an absolute convergence. So this is how we need to prove converse of Abbo theorem is not true. So you need to remember this concept also. They can ask for 2 marks. Is every convergent series absolutely convergent? Then you need to give a counter example. You need to say that it is not true, and here is the counter example. So you need to give this counter example, and you need to satisfy Leibniz theorem, 2 conditions of Leibniz theorem, and after that you need to show that it is absolutely convergent. Sorry, absolutely not convergent. It is conditionally convergent. Okay, so let us solve some examples on this absolute convergence and conditionally convergence. So test the convergence and absolutely convergence of the given series. See what they are given. Test the convergence as well as absolutely convergence of the given series. So here this is the series 1 minus 1 divided by 3 plus 1 divided by 5 minus 1 divided by 7 and so on, right? So summation un, how they are given, that you need to write. So summation un is equals to summation over n is equals to 1 to infinity. What they are given? Alternately they have given plus minus. Therefore minus 1 whole raised to n minus 1 divided by 2n minus 1. So all the denominators are odd terms, 3, 5, 7. So therefore minus 1 whole raised to n minus 1 divided by 2n minus 1 will get. So it is an alternating series, right? So here you need to consider un as well as un plus 1, and next you need to check that whether Leibniz theorem conditions are satisfied or not, right? So first un, consider un 1 divided by 2n minus 1, and un plus 1 will be 2n plus 1, 1 divided by 2n plus 1. So since 2n minus 1 is less than 2n plus 1, obviously 2n minus 1 is less than 2n plus 1 only. So if I take reciprocal, definitely this restriction will be reverse. 1 by 2n minus 1 is greater than 1 divided by 2n plus 1. This is true. This is true for all n. So therefore un is greater than un plus 1. Un is greater than un plus 1. First condition of Leibniz theorem is true. And next, second condition is what? Limit as n tends to infinity, un is equals to 0. So check it out whether we'll get 0 or not. Limit as n tends to infinity, un is equals to, what is our un? 1 divided by 2n minus 1. So limit as n tends to infinity, 1 divided by 2n minus 1. This will be 1 divided by infinity will get. So 1 divided by infinity is 0. So second condition is also true. Therefore by Leibniz test the series is convergent. So first case is over. Test the convergence. So the given series is convergent, we have proved it. But what we need to show that? Still we need to show that it is absolutely convergent. So absolutely convergent means you need to put modulus, that's it. So modulus of un, if you consider 1 divided by 2n minus 1 only will get, right? modulus of un. Un is how we have taken 1 divided by 2n minus 1. So modulus, apply the modulus, same thing will get 1 divided by 2n minus 1, and which is greater than 1 by 2n for every n, right? So since summation 1 divided by 2n is equals to 1 divided by 2 into summation 1 divided by n, it is divergent. It is divergent. Why it is divergent? It is in the form of p series, harmonic series, and p value is here 1. So therefore, according to p series, the given series 1 divided by n, summation 1 divided by n is divergent. Hence, summation un is conditionally convergent, not absolutely convergent. It is conditionally convergent. So this is how we need to show, we need to solve the examples on absolutely convergence, as well as what I can say that conditionally convergent, right? So same procedure you need to follow for all these examples. Same procedure, you need to check that whether conditions of Leibniz theorem satisfied or not. If it is satisfied, then you need to go further. If it is not satisfied, directly you can say that it is not an alternating series, right? So this is how you need to solve. So I will stop here. Just go through these examples. You will get to know how we need to solve such type of problems. Okay. If you have any doubt, you can message me or you can contact me. Okay. Thank you.